Alright, so we stopped by looking at the resistance network. I should qualify it by saying thermal resistance network for composite wall. So that's where we stopped in the last lecture. So supposing there are multiple walls which are associated. So if the length is L1, L2 and L3, and we have fluid which is flowing on either side of the composite wall. So that's the composite wall. Okay. And so if the conductivities are Ka, Kb and Kc, so we said that we could construct a network which has essentially five resistances. That's x direction, and if the heat transport coefficient is H1 on this side and the temperature is T infinity 1 and this is H2 and T infinity 2. So we said that it's T infinity 1 and T infinity 2, and the resistances are 1 by H1A, L1 by K1A, L2 by K2A and L3 by K3A and 1 by H2A. Okay. So one could define, we know what is the total resistance. So the total resistance, R total, will simply be sum of all the resistances, sum of all the individual resistances, which is essentially sum of these. Now what we are going to start with in today's lecture is we are going to look at what is called the overall heat transport coefficient. Okay. So one could define an overall heat transfer coefficient, and the reason for doing that is ultimately from measurement point of view. In practice, what I would measure is the temperature here and temperature here. So I need to know what is the total amount of heat that is transferred from, let's say, hot fluid on this side. Oh, I use 1. Okay, so I can put 1, 2 and 3. Okay, and cold fluid on this side. Okay. So I want to know what is the effective heat transport that has occurred from the hot fluid to the cold fluid, and that is simply because I may not be able to measure the temperatures in between. So one could define the total amount of heat that is transported similar to the way we defined using Newton's law of cooling as the constitutive equations. So we could write define an overall heat transport coefficient U multiplied by A multiplied by the net temperature difference of the observable temperatures or measurable properties. Okay. And that should obviously be equal to, what? Yeah? By R total. So that's right. So that should be equal to T infinity 1 minus T infinity 2 divided by R total simply by the definition of the resistances. Okay. So from here we can clearly read out that R total equal to 1 by UA, okay, and that should be equal to the sum of the individual resistances, sum of all the resistances that is involved in the system that we are considering. So this is a ubiquitous property of or definition of any heat transport system. So in principle one could define an overall heat transport coefficient for any heat transport system, and what we are doing essentially is we are lumping all the properties, all the transport processes which are occurring inside, everything is lumped into this one quantity called universal or overall heat transport coefficient. And we will see many different variations of the overall heat transport coefficient depending upon the system that you are considering. that we are going to see in today's lecture and several lectures in future. So it's very important to understand the definition of overall heat transport coefficient, and note that it's a fictitious quantity. It can be detected based on the individual properties of the system that you are considering. However, overall heat transport coefficient is mainly for convenience purposes and for calculation purposes. It really helps in defining such kind of a quantity. Okay. So there is one small aspect about resistances. There is something called contact resistance. So far in all the couple of examples that we described in the last lecture and start of today's lecture, we assume that the contact between the slabs is supposed to be a smooth contact. However, in reality that need not necessarily be the case. For example, if you have when you say smooth, it's smooth all the way up to the microscopic level, right? So it's not the smoothness that you observe in your eyes, it's the smoothness that you would observe when you see under a microscope. So that you will not expect. There's no reason why you should expect that the wall that you are having has a smooth surface all the way up to the microscopic level. So therefore there will always be certain resistance which is offered by the non-smooth contact between the two surfaces of the composite wall. So as a result, one could define something called a contact resistance, and it depends upon the smoothness properties. So there is no clean way to estimate what should be the value of this contact. There are some correlations. We will not go into those correlations in this course, but as and when it is required, particularly from the problem solving or exam point of view, these kinds of numbers will be provided to you. Okay. So give me a second. So supposing if you have another wall here, okay. Now if I want to construct the resistance network including the contact resistance, then what I would do is, so supposing I have fluid which is flowing here, okay, then you will have, so in addition, if there is no contact resistance, then there are total of 5 resistances, but because the contact position is not smooth, it is going to offer a certain resistance to heat transport, and therefore you will have an additional network which is basically the contact resistance, which will come in series. So the other 5 are the same thing what we saw a short while ago. So we need to include a contact resistance which is present in between. Supposing we want to include a contact resistance between the second and the third wall, we could do that. We could include another resistance here. Any questions? Correct. Yeah. So supposing if they are not in contact with each other, okay. So a very simple example is, supposing you are holding a coffee cup, okay. So there are 2 ways of holding it. I could hold it like this with all my fingers on the curved surface of the tumbler, or I could hold it just at the top. So if you look at the workers who are like drinking coffee and tea, the hot tea, they usually hold the tip or they hold a cup like this. And the reason is that you do not want to have a direct contact with the surface which is hot. Now taking that parallel here, if the surface is not smooth, then the contact, the transport of heat from one slab to the other depends upon the overall effective surface area which is available for transport. Now if the contact is not very smooth, then the total surface area which is available for heat transport from one slab to the other slab is not as much as the overall surface area which is available, and therefore the total amount of heat that is transported is not exactly the amount of heat that comes at this end, and therefore this offers a resistance. Yes, you had a question? Yes, there will be a dissipation because of that. See, what is the resistance? Note that the resistance is basically characterizes the total amount, the ability of the system to transport heat. What is the resistance that it offers to transportation of heat from one location to the other? Because the contact point is not significantly good, there is going to be some dissipation, and therefore that offers a certain resistance, and that's what is captured by the contact resistance. Okay. Any other questions? Okay. Alright, so next what we are going to see is, we assumed so far in all the cases that we considered that the area of heat transport is constant. So today we are going to look at the varying area systems. So how to characterize and quantify conduction process through a system where the surface area or cross sectional area for heat transport is constantly changing. Okay. A very simple example would be that, supposing I have a truncated cone, okay. I have a truncated cone, okay, and let us say I am looking at, so this is let us say at equal to 0. Okay. So I want to know what is the heat that is being transported from, let us say, let me call this as x direction, x equal to x1, x2, I wanted to call it radius. So that is the center, so the radius is 0. So I want to know what is the amount of heat that is transported from x1 to x2, and I am going to make an assumption, because I am looking at 1D systems, I am making an assumption that the cross sectional temperature that means that at every cross section I assume that the temperature is uniform in the cross section and the gradients are 0. Okay. So now, so this is my radius at any location, and so I could write my balance, and if I continue to assume that it is a steady state system and heat generation is 0, same assumptions as what we made before. So I could simply write the total amount of heat, the heat transfer rate Qx is given by minus K, which is the conductivity of that material, multiplied by the cross sectional area of heat transport. So note that now the cross sectional area is a position of the function, is a function of the position, excuse me, okay, multiplied by dt by dx. Okay. So what is the objective? We need to find the temperature profile. That is the objective of the problem, right. So we said that if we know the temperature distribution, if we know the temperature profile, we are done. We have quantified the system. So that is what we need to find. So let us say we integrate this equation, okay. So we say that Qx is minus K. What is the area? It is pi, cross sectional area is pi into radius square, okay, pi r square, right, multiplied by dt by dx, right. So supposing I say that r goes as a linear function of the position, if I say that the radius of the local radius goes as a linear function of the axial position, then I could simply rewrite this as minus K pi a square x square into dt by dx okay. And now what will be Qx? Will it be constant or it will change? Rate of heat transfer, that will be constant. Why will it be constant? Because of the energy balance, you see that there is no heat that is being generated. So whatever comes in has to go out here at steady state conditions. Note that steady state is very important. Yes. Right. So the question is, if you have dissipation of heat, how will it be constant? But when we say that there is no generation or loss of heat, which means that the dissipation is 0. We will come to that. So there are ways to consider that. We will actually consider when you are doing a two-dimensional system, you can actually look at dissipation from the outside walls, and we will actually see it in one of the examples in the future lectures. Alright, so because Qx is constant, we should be able to integrate this expression to find the temperature profile. So supposing I integrate between T1 and T, T1 is the temperature at the boundaries of this system, okay, T1 is the temperature at the boundaries of this system. I integrate between T1 and T, that's equal to Qx minus Qx by k pi r square of k pi a square into dx by x square going from x1 to x, okay. That is a pretty simple integration. So, it is Qx by k pi a square into 1 by x minus 1 by x1, okay. So, note that because it is 1 by x square, the minus sign will go away because of the integration, okay. And this is T minus T1, okay. So, therefore, T is T1 plus Qx by k pi a square into 1 by x minus 1 by x1. Is it a complete description? We do not know the Qx value, right. So, it is not a complete description yet. So, how do we find Qx? So, we know that the temperature in the other boundary is T2. So, we can use that property to find out what is Qx. So, we do not know what Qx is. So, how we are going to do that? We are going to say T2 is T1 plus Qx by k pi a square multiplied by 1 by x2 minus 1 by x1, okay. So, from here Qx is given by T2 minus T1 divided by 1 by x2 minus 1 by x1 multiplied by k pi a square multiplied by k pi a square. And so, now we can plug this into our solution. We can plug this into our solution. So, T equal to T1 plus k pi plus T2 minus T1 divided by 1 by x2 minus 1 by x1 multiplied by 1 by x minus 1 by x1. So, that is the distribution, temperature distribution in the system with the varying cross sectional area. So, an important message of this example is that what you need, what is preserved here or what remains constant in this system because there is no heat generation or dissipation is the heat transfer rate and not the flux, okay. So, you have to make a distinction here. So, what we said is the heat transfer rate so this remains a constant. However, the flux which is given by Q prime which is minus k dt by dx, this is not a constant. So, this is an important observation which you would not have made in the simple 1D system where the cross sectional area is constant. The cross sectional area of heat transport is constant, where you would not be able to make such a distinction between the two. So, when you have varying cross sectional area, what is really conserved and what is really preserved is the heat transfer rate, and in fact that is the reason why you write a rate balance and not a flux balance. So, this is very important to understand this distinction. It is important to write a transfer rate balance because that is the final quantity that is of importance, and the flux need not necessarily remain constant even in a small element. So, it is very important to understand these distinctions, and we are going to next see how these things are going to play a role when you are looking at radial systems where this becomes extremely important.